So far in our discussion of ray diagrams for both types of spherical mirrors, we've talked about whether images wind up being real or virtual, whether they're upright or upside down. We even got a little bit of an intro into whether they're magnified or reduced, um, based on how your image arrow is oriented and sized and positioned compared to um, the object arrow that we had drawn. We've also talked about images in terms of focal length and distances d and d prime, so how far the object is and how far the image appears, and the heights h and h prime, which would be however tall your object is, and h prime however tall it appears to be. So you could just keep going on doing ray diagrams, hoping that everything is exactly parallel to the principal axis and that you're getting everything set up just the right way. But for those of us that are a little more into equations, there are two formulas that relate all of these variables to each other. And if you use them properly, you can tell whether an image is real or virtual, upright, upside down, and you won't ever have to draw another ray diagram. Well, actually we will when we get to lenses, but once we get through that, if you don't like to do it, you don't have to do it. So there are two formulas, and they're all the math that you'll have to know when you're dealing with this geometric optics stuff. So when you're trying to figure out images for mirrors and lenses. So the first equation is the one that relates focal length, distance of an object, and distance of an image. Um, So that looks like this. 1 over f equals 1 over d plus 1 over d prime. So just remember that f is your focal length, d is the distance to the object, well, between the vertex and the object, and d prime is the distance between your vertex and where the image is forming. So anytime you run this equation, values of d, d prime, and f are positive if they appear in front of the mirror. So whichever side is reflective. If you're in a concave mirror, it would be the curved inside. Convex mirror would be um, the bulging outside. And then if they are behind the mirror, then they'll have negative values. So obviously an object can't be reflected unless it's in front of a mirror. So we know that d, the distance between the object and the vertex, should always be positive. No, why'd I rotate it? I can't get it to go back. Alright, so your 1 over d should always be a positive term, but we've seen in some cases that the focal length will be negative, and that's when we talked about convex mirrors. And d prime will be negative, also for convex mirrors, and for concave mirrors, but only when the object is closer than the focal point. So anytime we have a negative value of d prime, that's going to tell us, big red flag, that we have a virtual image. A positive value for d prime will always let us know that we're working with a real image. So negative because it's behind the mirror. We already know if an image exists behind the mirror, it has to be virtual because it's not being created from the actual reflected rays. So a normal flat mirror is just effectively a convex mirror with a really far away focal point, infinitely far away. So the light rays never converge. If you set 1 over f to 0, so 1 divided by a really huge number, then we get what we would expect. The image appears to be as far away from the mirror as the object is. If you've ever looked in front of a mirror, you can tell how much distance there is between you. And also we know that it would be virtual because the positive here and same size negative would give us the 0 that we expect. Okay, our next equation is the one that's going to tell us about magnification. These notes packets use a little m. More likely you'll see a capital M like in the equation here. So magnification is equal to image height over object height. It's also equal to negative image distance divided by object distance. So you have to be careful here. H prime values are going to be positive if the image is upright. If you get negative values for H prime, that means that your image is inverted upside down. The value of the magnification is always going to be a positive because the object always has to be upright. That one is actually an error here. That should say the value of H will always be positive because the object always has to be upright. So you might want to scratch that out and forget the last thing that I said right before this. The value of H is always positive because the object itself is always upright. Alright, so here we go. The magnification tells us how large the image will be with respect to the object. So if we have an absolute value of m that's bigger than 1, then that means the image that's forming is actually bigger than 100% of what it should be. It's magnified. But if absolute value of magnification is less than 1, then we know that it's going to come out smaller or reduced. And then last thing that could happen if m is equal to 1, so like an ordinary flat mirror or a couple instances you saw with the concave mirrors, then we know that the image is the same size as the object. Because rays move in straight lines, the closer that an image is to the mirror, the larger it's going to appear. So d prime over d is always going to have a positive value with virtual images. Remember, you'd plug in a negative distance if it's forming behind the mirror. D always has to be positive. We said it has to be in front of the mirror. So negative, negative would cancel out. It would be positive. If you're working with a real image, then you'll have a positive d prime over a positive d, and the negative would turn the whole thing negative. So accordingly, the image appears upright with virtual images when m is positive, and the image appears upside down with real images where the magnification is negative. Alright, we'll run through one example and it should wrap up this video. We have a woman standing 40 centimeters from a concave mirror, and it has a focal length of 30 centimeters. How far from the mirror should she set up a screen in order for her image to be projected onto it? If she's 1.5 meters tall, how tall will her image appear on the screen? So this is asking us two different questions. We'll split it up into two different parts. First, we want to know how far from the mirror should she set up a screen for her image to be projected onto it. This question is asking us to find at what distance will the image form. Alright, so we know we'll be using 1 over f equals 1 over d plus 1 over d prime. So if we plug in the values that we have, we'll have 1 divided by, just gonna keep it centimeters. 1 divided by 30 centimeters is equal to 1 divided by 40 centimeters because she's 40 centimeters away, plus 1 divided by d prime. That's what we're trying to find here. So we go through here, 1/30th minus 1/40th. That'll leave us with 1 over d, so we invert what we get there and have d prime equals 120 centimeters. So we've satisfied the first question it asks, how far away should the screen be? She should place it at 120 centimeters. Now for the other part, how tall will her image appear on the screen? So we'll be using our other equation here for magnification. So we want to know how tall will the image be. So we're looking for h prime. Our equation looks like h prime divided by h. We know her height. We're looking for the image height. We actually don't know the magnification yet, so we'll have to use the other part of the equation first. Negative d prime divided by d. So we know both of these things. So we have negative 120 centimeters, that's the value we just found, divided by, what was hers? She's 40 away. Alright, so we find that the magnification is -3. So how tall will her image appear? -3 equals h prime over h. And we know her actual height is 1.5 meters. So -3 times 1.5 is -4.5 meters. So when the question asks how tall will her image be on the screen, really that's just asking for the height. So we know it's going to be 4.5 meters tall, but from our answer we also know since it's negative, it will be upside down.